Just because you haven't found your talent yet, it doesn't mean you don't have one. Actually, every individual is born with some qualities. So you need to find that one quality which you can work out on and improve upon. So, students, believe in your abilities, have that confidence to excel, and certainly and surely you will achieve what you desire for.
जय हिंद स्टूडेंट्स, हाउ आर यू ऑल? आप लोग कैसे हैं? आई होप यू ऑल आर फिट, फाइन एंड इन जोवियल मूड. You must be enthusiastic towards your studies. So with that note, let's start today's session. Today we will be discussing scattering of light. It's a very important phenomenon. Look, imagine Earth's atmosphere to be absent. If the atmosphere of the Earth is considered to be not present, in that case, light would have not got scattered, it would have not interacted through the constituent particles of the Earth's atmosphere, and in such a scenario, it would have appeared dark, complete dark, from the outer space. So anyway, we'll discuss these things in detail. Then we will also discuss in this session the blue color of the sky, the red color used as a danger signal, that during sunrise or sunset, the sun appears to be reddish. So these are all concepts which we will be covering in this particular session, right? These all natural phenomena are based on scattering of light. So before we start with the actual topic, I would like you to watch this clipping. Again, I've added this clipping just to make this teaching much more interesting and enthralling experience for you. Watch this clipping.
Scattering of light. When a beam of light falls on an atom, it causes the electron in the atom to vibrate. The vibrating electrons in turn re-emit light in all the directions. This process is known as scattering of light. Earth's atmosphere contains air molecules and other tiny particles. So when light from the sun passes through the Earth's atmosphere, it gets scattered by the large number of particles in the atmosphere. Lord Rayleigh studied the scattering of light in detail. He observed that the amount of scattering suffered by different wavelengths of light is different. He found that the intensity of a particular wavelength in the scattered light depends greatly on its wavelength, and ultimately he formulated the following law. As per Rayleigh's law, the intensity of the scattered beam corresponding to a particular wavelength varies inversely as the fourth power of the wavelength. These are the 7 colors of white light and blue, indigo and violet. These colors have short wavelengths. So as per the law, these colors should get more scattered. This is the reason for the blue color of the sky. But wait, since violet has minimum wavelength, so why doesn't the sky appears violet, or for that matter indigo, instead of blue? So the reason is, this is the solar spectrum, which is composed of 7 different colors. It clearly shows that the sunlight consists of blue color in larger amount as compared to that of violet color. So as a result, blue color get more scattered, and as a result, the sky appears to be blue. There is another reason. Our eye is sensitive more to blue color than violet.
Okay friends, I hope you have enjoyed watching this clipping and you have understood the concept of scattering of light. But again, I would like to recapitulate all the topics which we have just now watched in the short clipping, right? So, scattering of light, what we have discussed is, light gets scattered only when it interacts with the constituent particles of the atmosphere, right? So when light passes through the Earth's atmosphere, what happens is, it gets absorbed by the atoms, and then the light gets re-emitted in all the directions. This phenomenon is known as the scattering of light. Actually, when a beam of light falls on an atom, then the electrons in the atom starts vibrating, and as a result it emits, or rather it re-emits light in all the directions. So this is scattering of light, right? And as we have discussed in that short video, Lord Relic, he was the first person to have studied the scattering of light in detail. And he found that different colors, different wavelengths, while passing through the Earth's atmosphere, get scattered through different amounts. So he experimentally studied the scattering of light in detail and formulated a law which is known after his name as Rayleigh's law of scattering. And what's the statement of this law? According to the Rayleigh's law of scattering, it states that the intensity of light corresponding to a particular wavelength in the scattered light varies inversely as the fourth power of the wavelength of the light. That is, mathematically, I is inversely proportional to the fourth power of the wavelength. This is Rayleigh's law of scattering. I is the intensity of the light corresponding to a particular wavelength in the scattered light. It is inversely proportional to the fourth power of the wavelength of the light. So it clearly suggests that shorter the wavelength, more will be the scattering of that particular wavelength. And longer the wavelength, lesser will be the scattering of that particular light. Right? And I would like to mention that Rayleigh's law of scattering, this is valid only when the light gets scattered through extremely small particles. When the light gets scattered through large particles like dust particles or like water droplets, then Rayleigh's law is not valid. So, the light gets scattered as per this law only when it gets scattered through molecules which are of extremely small size. Right? So this is Rayleigh's law of scattering. We have also discussed the consequence of this particular law, right? Rather, we have discussed the applications. We all are aware the solar spectrum. It consists of 7 constituent colors, that is Vibgyor. So this is violet, indigo, blue, green, yellow, orange and red. Now we are also aware of the sequence. It's arranged in a particular manner in order of the increasing wavelength. So the wavelength of red color is maximum while the wavelength of violet color is minimum. So in the visible spectrum, red color possesses longest wavelength while violet color possesses smallest wavelength. So as per this, red being longer wavelength, it will get least scattered, while violet, its wavelength is smallest in the visible spectrum, so violet color must get scattered to the maximum extent as per this law. Is it clear, students? Okay, now what we discussed is its application, and first application was the blue color of the sky, right? So I will explain it mathematically, right? So here, as you are aware, this is in the increasing direction of wavelength. That is, violet possesses minimum wavelength, red it possesses maximum wavelength. Actually, it is found that the wavelength of the blue color is equal to half the wavelength of the red color, right? The range of the wavelength in the visible spectrum is about 3900 angstrom to 7600 angstrom. It lies in this range, 3900 angstrom to 7600 angstrom. And here angstrom is, 1 angstrom is 10 raised to power minus 10 meter. SI unit of wavelength is meter. So this is the range of the visible spectrum. And it is found that the wavelength of the blue color is half the wavelength of the red color. So make use of this over here. So what you do is, for blue color, it will be proportional 1 by lambda b4, and intensity of the scattered light corresponding to the red color, it will be proportional to 1 by lambda 4 of red color, right? If you divide these two, what you get is IB divided by IR. Proportional sign will get eliminated. So what is left is lambda R4 divided by lambda B4. That is lambda R divided by lambda B to the power 4. Now look, lambda R is equal to twice of lambda B. So here we can write twice of lambda B to the power 4 divided by lambda B. Lambda B gets cancelled. So we are left with 2 raised to power 4, which is equal to 16. That is IB, it is equal to 16 times IR. So what it suggests is blue color students, it gets scattered 16 times more than that of red color. So that is the reason why blue color predominates and the sky appears to be blue. Now one question may arise in your mind, that if the wavelength of violet is smaller, or for that matter indigo is smaller than that of blue color, then why doesn't the sky appears violet? This must be the question arising in your mind. The reason I have already explained in that short video. I'll again explain it. There are 2 reasons for it. Why this sky doesn't appear violet, or for that matter indigo instead of blue. Instead of the fact that violet and indigo both have got shorter wavelength than that of blue. So the explanation lies in the fact that solar spectrum, as you are aware, it consists of these 7 colors. The amount of blue color in the sunlight is far more as compared to the violet and indigo. So that's the first reason why the scattering of blue color is much more. It predominates. Blue color predominates. And the second reason is, students, our eye, its sensitivity is different for different wavelengths or different colors. It is more sensitive, it is most sensitive to the green color. But out of blue and violet indigo, it is more sensitive to blue color as compared to violet or indigo. So these are the 2 basic reasons why the sky appears to be blue. So I hope you have now understood the concept behind it, right? So let's discuss the second application as well. You have done this one, blue color of the sky. Let's discuss why red color is used as a danger signal. Now students, it's a common sense that which color would you prefer as a danger signal? Obviously, that color will be preferred which can be seen distinctly and clearly, even through a distance, even from a faraway distance. So what I mean to say is that the color which get least scattered through the Earth's atmosphere, that color is to be used as a danger signal. Now as we have discussed, intensity of light corresponding to a particular wavelength as per Rayleigh's law, it is inversely proportional to the 4th power of the wavelength. So the wavelength of the red color being minimum, or rather the wavelength of the red color being maximum, the wavelength of the red color being maximum, red color get least scattered. So this is the very reason why red color is used as a danger signal. So because of the long wavelength of the red color, it get least scattered. Therefore red color, even when observed from a distance, it can be seen distinctly and clearly. So that is the reason why we make use of red color as a danger signal. Right? Okay, next application again. Sun appears reddish during sunrise and sunset. So this I will explain with the help of a diagram. So what we do is, we are all aware during sunset or sunrise, the sun is near the horizon, right? So it can be diagrammatically shown in the following manner. this is suppose the observer, and this can be considered to be the horizon. It's represented by the dotted line, tangent at point O, right? This is the horizon. And suppose this is the Earth's atmosphere. This is the Earth's atmosphere. Obviously, Earth's atmosphere is composed of gases, dust particles, water droplets, right? And 78% nitrogen, 21% oxygen, 0.03% carbon dioxide, and small traces of neon, helium, argon, isn't it? Dust particles and all that. These all constitute Earth's atmosphere. So during sunset or sunrise, the sun is near the horizon, like this. Sun is at a far away distance, so therefore it is shown smaller, right? So this is sun, it is near the horizon. This is during, suppose, sunrise. And during sunset, sun would be at this particular position, again near the horizon, right? So let's consider one of the two positions, either sunrise or sunset. So during sunrise or sunset, the light from the sun entering the Earth's atmosphere has to traverse this much distance. Suppose it is x through the Earth's atmosphere, right? This is the distance x which is covered by the light coming from the sun through the Earth's atmosphere during sunrise or sunset, when the sun is near the horizon, right? This is the distance. Okay, now imagine the sun to be at the overhead position during noon. So during noon, the sun would be at the overhead position like this. So in such case, the light coming from the sun would travel, say, distance y through the Earth's atmosphere, right? This is at noon, when the sun will be at the overhead position. The sun will be at the overhead position. I think you have understood the diagram, right? It doesn't need any explanation. The diagram is actually self-explanatory in the sense that during sunrise or sunset, when the sun is near the horizon, the light from the sun has to cover larger distance through the Earth's atmosphere as compared to the case when the sun is at the overhead position during noon. So it's pretty clear. X is greater than y. So students, what happens is, in this case, when the light has to traverse larger distance through the Earth's atmosphere, all the blue light gets scattered away. It gets scattered away. So only the light of longer wavelength is able to reach the observer's eye. And light of longer wavelength is red or orange or red. So that is the reason why during sunrise or sunset, only the light of longer wavelength tends to reach the observer's eye. As a result of which, the sky or sun appears to be reddish. So this is the reason behind it. I hope you have understood this concept, right? Okay, last one. White color of the cloud. First students, here, I must mention, I've already mentioned it earlier, that Raleigh's law of scattering, or rather light gets scattered obeying Raleigh's law only if the light gets scattered through extremely small molecules, right? In case of clouds, it contains water droplets and dust particles which are quite of large size. So in that case also light gets scattered, but the amount of scattering of different wavelengths is found to be same. We do not obey Raleigh's law of scattering. So different wavelengths get scattered through same amount. And as a result, again, white light tends to enter our eye. So as a result, cloud tends to appear white. Clear? So here Raleigh's law is not valid when scattering takes place from large molecules. So I hope these all concepts are pretty clear, right? So now I would like you to watch again a shock clipping based on Tyndall effect. It is also an effect or a phenomena based on scattering of light. when light passes through colloidal particles. So let's first watch this short clipping, and then again I will try to recapitulate that particular topic. Right, students?
Light from the sun is everywhere, but its path is not visible to us. When light enters a smoke-filled room, then its path is visible. Can you state the reason for this? Yes, the reason is scattering of light. The smoke-filled room, it contains dust particles through which the beam of light gets scattered. And these small solid particles suspended in a fluid are known as colloidal particles. This phenomena of scattering of light by the colloidal particles is known as Tyndall effect. Tyndall effect can also be observed when sunlight passes through a canopy of a dense forest. Here, tiny water droplets in the mist scatter light. Now let us perform an activity. Place a strong source S of white light at the focus of a converging lens L1. The lens provides a parallel beam of light. Allow the light beam to pass through a transparent glass tank T containing clear water. Allow the beam of light to pass through a circular hole C made in a cardboard. Obtain a sharp image of the circular hole on a screen Mn using a second converging lens L2. The path of beam of light passing through the true solution is not visible. Now dissolve about 200 gram of sodium thiosulfate hypo in about 2 liter of clean water taken in the tank. Add about 1 to 2 millimeter of concentrated H2SO4 to the water. Let's see what we observe. We will find that fine microscopic sulfur particles precipitating in about 2 to 3 minutes. As the sulfur particles begin to form, you can observe the blue light from the 3 sides of the glass tank. This is due to the scattering of short wavelengths by minute colloidal sulfur particles. Observe the color of the transmitted light from the 4th side of the glass tank facing the circular hole. It is interesting to observe at first the orange-red color and then bright crimson-red color on the screen.
So students, I hope you have enjoyed watching this visual clipping based on Tyndall effect. The concept must be clear, and we have discussed an activity as well, isn't it? So that was very, very important. So let me recapitulate all the things which we have watched in that clipping. Tyndall effect actually is the scattering of light. When the light gets scattered through colloidal particles, right? And also we have discussed that it is only when the light gets scattered then its path is visible. Light is all around us, but its path is not visible. It is visible only when it gets scattered. And for scattering, small smoke, dust particles are required. Right? And here I would also like to mention there is a basic difference between reflection and scattering. During reflection, what happens is the light is incident on a reflecting surface and it gets reflected or bounced back into a particular direction. But students, in scattering, what happens is light falls on an atom, it gets absorbed, the electron starts vibrating, and it re-emits the light in all the directions, So that is scattering of light. Right? So Tyndall effect is the extension of scattering of light only, nothing new in it. So with the help of Tyndall effect also, we can easily explain the blue color of the sky, then the appearance of reddish or orange sun during sunset or sunrise. Right? So students, I hope you have enjoyed this particular session. So please watch this video again and again till you understand each and every minute concept. Right? And I will conclude this session by sharing a very important information with you. Sir C. Raman, he studied the scattering of light by molecules, and that effect is known as Raman effect, and he was awarded Nobel Prize for that.
So students, let's conclude this session. Do join me in my next lecture then, and don't forget to like, share, comment, and eventually do subscribe my channel and share the link with your friends.